Hello, once again. Welcome to the second lecture of digital communication. In previous lecture, we have studied about that what is digital communication, why digital communication it is important, what are the different advantages and disadvantages of digital communication over analog communication we have seen. Then we have seen that what are the different blocks involved in digital communication system, and we have seen the details of each block. After that, we have seen that what are the different nomenclature that has been used in digital communications. Now moving to the next part, the today's topic we are going to start with is a sampling theorem. Now, as we know that broadly, there are two types of signals, continuous time signal and discrete time signal. So, due to some recent advanced development in digital technology, the inexpensive, lightweight, programmable, and easy reproducible discrete time systems are easily available. So, therefore, processing of discrete time signals is much more flexible as compared to analog signals. So it means although we have a large number of continuous time signals, but we prefer processing of discrete time signals. So for this purpose, we are able to convert a continuous time signal into a discrete time signal. And this problem is solved by the fundamental mathematical tool known as sampling theorem. So, sampling it is a process of converting continuous time signals into equivalent discrete time signals by taking the samples at discrete time intervals. Sample makes analog signals discrete in time, but still it is continuous in value. And if sampling it is done properly, that is, if Nyquist theorem it is satisfied, then sampling doesn't introduce any distortion. You can see on this screen that here it is sampling it is there, waveform it is there. You can see that this is an analog input signal and this is a continuous train of unit impulse, and when the multiplication of this analog signal and this sampled pulse train signal it happened, then resultant wave you would get the sampled output as you can see on this screen. So it is nothing but your sampled output signal. Now, what is sampling theorem? So basically, sampling theorem, it is a continuous time signal that may be completely represented in its samples and recovered back if the sampling frequency, that is fs, is greater than or equal to twice of fm. Now, what is this fs and what is this fm? Here, fs is nothing but your sample frequency, and fm it is the maximum frequency present in the signal. In sampling theorem, there is a most important term that is called a Nyquist theorem. It is there. So what it tells, Nyquist theorem, it provides a prescription for the normal sampling interval required to avoid aliasing that we are going to see in a moment. Now, Nyquist theorem, it may be stated that as follows: the sampling frequency fs, it must be at the rate equal to or greater than twice the highest frequency component fm present in the signal. That is, fs, it should be greater than or equal to twice of fm in order to recover your signal exactly. Now, when the sampling rate becomes exactly equal to twice of fm, then it is called a Nyquist rate. And this Nyquist rate, it is also defined as a minimum sampling rate that is we require. So it is given by fs is equal to twice of fm. Now, similarly, the maximum sampling interval is called as Nyquist interval. It is given by Nyquist interval Ts is equal to 1 upon 2 fm second. Next, now the restriction of this fs that is greater than or equal to twice of fm stated in terms of the sampling rate. It is known as the Nyquist criterion. The Nyquist criterion is theoretically sufficient condition to allow an analog signal to be reconstructed completely from a set of uniformly spaced discrete time signals. Now, after that, we are going to see the sampling techniques, that what are the different sampling techniques are there. Now, there are three types of sampling techniques are there. They are impulse sampling, or we call it as ideal sampling, then natural sampling, and third one, it is called your flat top sampling. Now, moving to this ideal sampling or impulse sampling. Now, assuming this x of t, that is a continuous time signal as shown in figure, please see the cursor on the screen. And this is a Fourier transform, that was x of f, which is outside the interval, which is 0. Outside this interval, you can see that is from minus fm to fm. The sampling of this x of t, the sampling of this x of t, it can be viewed as the product of this periodic train of unit impulse function, that is x of del of t, with this x of t. So the resultant sampled signal, you are getting this one. So now, using this frequency convolution property of this Fourier transform, we can transform this time domain product of x of t and this x del of t to the frequency domain convolution of x of f to the x del of f. And this is the resultant sampled version of your signal. And here it is a circuit diagram of your impulse sampling. But this sampling, it has a demerits. Now, what is the demerits of that? You can observe from this figure the width of this impulse train, it is tends to 0. So due to this, what is going to be happen, the power content present in this instantaneous sampled pulse, it is negligible. So thus this method, it is not suitable for transmission purpose. So that's why, in order to overcome this disadvantage, we are moving to natural sampling. Now, as shown in this figure, the sampling of band limited analog signal, that is x of t, it is multiplied by this pulse train, that is of x of pt. And if you are going to see it, the width of the pulse, the pulse width, it is of duration t, and the amplitude of this pulse width, it is of 1 upon t. Now, this sampling, it is termed as a natural sampling. Why it is called a natural sampling? Now, if you will see the figure, that is the top of this sampled signal, it is equal to the, or it is going to retain the shape of this original or instantaneous value of this original signal. So that's why we are going to call it as a natural sampling. And if you will see this figure, this is a Fourier transform of this x of t, and this is the envelope of the magnitude of the spectrum of this pulse train, which is seen as a dashed line or dotted line. It has a characteristic of what? Sync shape. So using this frequency domain convolution of x of f and x of p of f, you would get this resultant sampled signal, and it is the circuit diagram for this natural sampling. Now, it is also some demerits. Now, what is a demerit? Demerit, it is that, as you have seen, that this sample data sequence, it has a varying top according to the signal variation. So during the transmission, what is going to be happen? The noise, it interferes on the top of the pulses. So then it becomes very much difficult to determine the shape of the top of the pulses at the receiver. So in order to overcome its disadvantage, the next, it is called, we are moving to this flat top sampling or sample and hold operation. Now you can see the circuit diagram of this flat top sampling or sample and hold operation. You can see that by applying a gate pulse to this G1, gate G1, which is called a sampling switch, it is closed for a small period. And during this interval, what is going to be happen? This capacitor, it is going to charge up to a voltage which is equal to the instantaneous value of this what x of t, that is incoming signal. Now, this sampling switch is now open. So as this open, the capacitor, it holds the charge, and after that, this discharge switch, it has been closed by applying a gating pulse to G2. So when this G2, it has been, this discharge switch, it has been closed, this capacitor, it is going to discharge through this one to the 0 volt, and this discharge switch is then open, and the capacitor, it doesn't have any voltage. So after the period of TS, this switch is closed again to make a new sample, and this periodic gating of sample and hold circuit, it is going to generate a sequence of flat top samples. So you can see this one from the graph, that this is your continuous time signal x of t, and this is your unit impulse train. Now unit, when you are going to multiply or do the convolution of x of t and the unit pulse, then you would get this what sampled one. Now after this one, the convolution of this sampled pulse train, that is x of t with x of del of t with this unity amplitude rectangular pulse. If you are see that third graph, it is what a unity amplitude rectangular pulse, which is of p of t. This has a pulse width of ts. Then if you are going to do the convolution of this unit pulse width with this one, then you would get this flat top sample version. If you will observe that the top of this pulse, it is flat, so that's why it is called as what flat top sampled sequence. Now in it, a very one more important concept it is there, that is called aliasing. Now what is aliasing? So basically, when a continuous time band limited signal is sampled at a rate lower than Nyquist rate, and what is Nyquist rate? That minimum sampling frequency, it should be equal to twice of fm. So if fs is less than twice of fm, then it is termed as what undersampling. So aliasing, it may be defined as a phenomenon in which a high frequency component in the frequency spectrum of the signal takes place the identity of the low frequency component in the signal. So you can see it in this figure, that how this aliasing, it has been taken place. When it is going to take place? When fs is less than twice of fm. So in this, the high frequency component, it has taken over this low frequency component, and due to which the information, it has been lost, or it is in ambiguous state. So that's why the Nyquist rate or Nyquist criteria, it is very much important, that at least sampling frequency, it should be greater than or equal to twice of fm. Now, the next topic that we are going to see, it is what? It is a quantization.
After sampling, the most important step is your quantization. So the quantization process, basically it is going to convert the continuous amplitude values into what? Finite, that is discrete set of allowable values. It converts from discrete time value signal to discrete time discrete value signal. Please note it down, that quantization, it is going to convert discrete time continuous valued signal to discrete time discrete valued signal. Here it is the figure of this quantization. There is quantization input, quantization noise, and it is a quantizer output, that y is equal to q of x. It is a function of your this input. Now in linear analog system, the transfer characteristic representing the relation between the input and output is what? Straight line. So for a quantizer, the transfer character, it is like staircase like appearance. And this quantization process, it has twofold effects. First is the peak to peak range of input values is subdivided into what? Finite set of decision levels or decision threshold that are aligned with risers of the staircase. Understood? It is aligned with what? Risers of the staircase. This is the first effect. The second effect is the output, it is assigned a discrete value that is selected from a finite set of representations levels or reconstruction values that are aligned with what? Treads of the staircase. Earlier it was what? Risers of the staircase. Now it is what? Treads of the staircase. So the combination of this sampler and quantizer is called analog to digital converter. Now, we would see the types of conversion. You can see that quantization, basically it is of two types: uniform quantization and non-uniform quantization. Again, uniform quantization, it is divided into symmetrical or uniform mid-thread type and mid-rise type. And in uniform quantization, basically it is a type of quantization in which the step size, it remains same throughout the input range. Whereas in non-uniform quantizer, in which the step size, it is going to vary according to the input signal values. So you can see from this figure that when the quantization levels are uniformly distributed over the full amplitude range of the input signal, the quantizer is called what? Uniform or linear quantizer. And in uniform quantization, the step size between the quantization levels, it remains same throughout the input range. It means it is constant. So from the figure you can see that it is a what? Mid thread type and it is mid rise type. So from this input output characteristic of this uniform quantizer, that is a mid thread type, you can see that the origin lies in the middle of the tread of a staircase graph. See, this is called as what? Tread. This is a staircase waveform and this is called what? Tread, and this vertical line, it is called risers. So you can see this origin, it is lies in the middle of the tread of this staircase graph. This is called tread. This is tread. So that's why it is called what? Mid tread type. Whereas this vertical line, it is called what? Risers of the staircase. So you can see the origin, this origin, it lies in the middle of the rising part of the your staircase graph. So that's why it is called what? Mid rise type. Understood? Now, if the quantization characteristic, if the quantization characteristic is non-linear, then the quantization is known as what? Non-uniform quantization. And in non-uniform quantization, the step size is not constant. It varies according to your input signal values. So the step size is variable depending on the amplitude of the input signal. So the non-uniform quantization is practically achieved through a process which is called what? Companding. And remember, companding is just non-uniform quantization. So this is required. You know why we are implementing this companding? In order to improve what? Signal to quantization noise ratio of weak signals, right? As we know that in uniform quantization, what we have seen, that once the step size is fixed, the quantization noise power, it automatically remain what? Constant. So however, but the signal power is not constant. It is proportional to the what square of the signal amplitude, and hence signal power it would be small for what weak signal, but the quantization noise power it would remain constant, and hence the signal to quantization noise ratio for this weak signal it would be what very poor. So if it is poor, then definitely it is going to affect the what quality of the signal. So what is the remedy? Remedy is to use what compounding. So this compounding, this is the figure that you can see the compounding model. That first it consists of your compressor, then uniform quantizer, and this is your expander. Input to the compressor and output we are taken from what expander. In this, what we are going to do it, that weak signals weak signals are amplified and the strong signals are attenuated before applying them to this uniform quantizer. So first compressor, what is going to do it, it is going to amplify the weak signal and it is going to attenuate what strong signals. So this process is called what compression, and this is the block, that is a compressor, it provides the compression. Now at the receiver, exactly opposite, it is followed, which is called expansion. And as you know, this is the circuit, this is the block of expander. The compression of the signal it is going to take place at transmitter, and expansion it is going to take place at the receiver. So the combination of this expansion and compression it is called as what compounding. See, the compression of the signal at the transmitter and the expansion at the receiver it is combined. So the compressing plus expanding together it is going to make a word what compounding. And basically this is achieved by two laws, that is mu law compounding and a law compounding. So you can see now from this graph, see this is the graph, it is going to show you the compressor characteristic. This is the relation between your input and output signal. Then you can see that compressor, it is going to provide the higher gain to weak signal, right? Whereas smaller gain to strong input signal, and hence the weak signals are artificially boosted to improve the signal to quantization noise ratio. And you can see this characteristic, right? And from the figure D, you can see for positive as well as for negative it has been shown. See how the compression it is going to take place positive side, and this is your negative side. Now similarly, now this is going to tell you your expansion characteristic. It is inversely, exactly, it is the inverse of the your compressor characteristic. So it is going to ensure that all the artificially boosted signals by this compressor are brought back to their original amplitudes at the receiver end. So this is the characteristic of your expander. So you can see from this waveform, from this graph, the characteristic of compression and expansion are exactly inverse. And this is a combination diagram. So in examination, you can draw this graph. And due to this inverse nature of your compressor and this expander, the overall characteristic, see this overall characteristic, it is shown by this straight line, dotted line, which is going to indicate what it is going to indicate, that boosted signals are brought back to their original amplitudes. And This, no, this non-uniform quantizer, it can be used to make the signal to quantization noise ratio, it is constant for all the signals within the input this range. And from this you can see that this is the characteristic how the step, it is vary according to the input signals. So this is the non-uniform characteristic. Now this is your mu law. So in mu law, from this graph you can see that basically mu law, it is used for what? Speech and music signals, and it is used for in PCM telephone system in US, Canada and Japan. So in this compressor characteristic, it is continuous, it is approximated linear for small values of your input levels, and whereas it is for logarithmic for high value of input signal. So we have drawn the graph for mu equal to 0. This is the formula for your mu law. So maximum mu that you can take it is 255, and this is the formula of your mu law. So we have considered the different value of mu. We have drawn the graph for mu equal to 0, for 5, for 255, and you can see that as the value of that mu it is going to increase, it is going to, the logarithmic characteristic, it is going to be shown. And this, from this formula, this is nothing but your sine function. It is an fx, it is nothing but your represent what? Output, right? And what is x? X, it is your input to the compressor. And remember this law, this compounding, it is used for music and speech signal. This is your normalized input, this is your normalized output. Second, it is your A law. So basically A law, it is used in PCM telephone system in Europe. So in this compressor characteristic is piecewise made up of linear segments. You can see that it is linear, over here it is a linear, but it is a piecewise, for low level of inputs, and for us high values of inputs, it is what? Logarithmic segment. This you can see it on the screen, and this is the formula for your A law. And we have plot this graph for A equal to 1. How would it look? For A equal to 2, and maximum value of A that we can take it is what? 87.56. So you can see it over here. So if compounding it has been asked, so it is necessary to draw this diagram for A law and for mu law. The next topic that we are going to see, it is what? Pulse code modulation. Now, when pulse modulation it is applied to binary symbols, the resulting binary waveform is called what? Pulse code modulation. Now, pulse code modulation basically it refers to the class of baseband signals obtained from quantized PAM signals by encoding each quantized sample into a digital word. And basically in PCM, what are the different operations that you can see? It is your sampling, quantizing, and most important is your encoding. So after encoding, you would get the pulse code modulation wave. So as we know, the process involves sampling, quantization, and coding, and each analog sample is transformed into a PCM word, which is made up of group of bits. So the PCM word size, it can be described by the number of quantization level which is allowed for each sample. Now suppose the number of quantization level is based on the what? The number of encoding bits required to identify the set of levels. So we know that the relationship between the size of a set of message symbol and the number of bits needed to present the symbol, it is what? M equal to 2 raised to k, as we already knew that if k equal to 1 it is there, then m equal to two possible values, 0 and 1. And if k equal to 2 it is there, then m it equal to what? 4. It could be 0 0 0 1 1 0 1 1, like that one. Similarly, for PCM, the relationship between the number of levels per sample and the number of bits needed to represent those level is given by what? Capital L is equal to what? 2 raised to L. And what is capital L? It is going to show you the number of quantizations level in PCM word, whereas small l, it is going to tell you what number of bits needed to represent those levels. So for examples, that if each sample has a 256 quantization levels, and then the bits per PCM word, we can, as you know, that capital L equal to 2 raised to L, and L, it is a number of quantization level, and that we know it is what? 256. So what would be the number of bits needed to represent those 256 levels? So definitely it would be what? Log of this, so it would be 8. Hence the number of bits needed to represent 256 quantization level, so small l, it would what? 8. So 8 bits we are going to require for this. Now this is the most important graph that you can see, that input range, it is excursion from its ranges from -4 volt to +4 volt, and this is the quantization level. See, that's -3.5, -2.5, -1.5 up to +3.5. And this is a code number, that is encoding. This is a code number that has been assigned to this. If the input, it is going to range from -3.5 to below this one, it is assigned a 0 value. But it is going to range from -3.5 to -2.5, it would be assigned a code 1. Similarly, this in this window, if 2.5 to +3.5, if any value it is going to come, then it would be assigned a code what? 7. Now, so we would see it. So this is the dotted, point on this one graph in your input. It is going to show you your natural sample value. See, it is a 1.3. What value it is? 1.3. So what is the quantized sample level? The quantized sample, it is nearer to what? 1.5. So since this 1.3, it is going to range from this 1.5 to 1.5, we are going to assign the code, that is what? 5. And what is the binary equivalent of 5? It is what? PCM sequence 101. So binary equivalent of 5, it is 101. So 1.3, it has assigned a value of 101. Similarly, now this, it has a value 3.6. What? It is 3.6, which is nearer to 3.5. So quantization level, it is what? 3.5. But it is going to come under the window of this 3 to 4, and the code word it has been assigned, it is what? 7. And what is the binary equivalent of 7? It is 111. Similarly, you can see it's the natural sample value, it is somewhat, it is what has a value 2.3. So which is nearer to this quantization level 2.5, and it has a code word what? 6. So what is the binary equivalent of 6? Is what? 110. Similarly, you can see it over here, natural sample point, it is a 0.7. So which is nearer to this quantization level 0.5, right? So this, you can see over here, so it has 0.5 quantization level, it has assigned a code word 4. So we have denote this value 4. And what is the binary equivalent of 4? It is what? 100. And similarly, we have done for these natural points also. So what I explained, that the step size between the quantization has been level, it has been set to 1 volt, and there are total 8 quantization level from -3.5 to +3.5, and we have assigned the code word to the level -3.5, then code 1 to -2.5, and 7 to 3.5, which I already explained. So hope so you understood this diagram, that how we are going to assign the code to the your any point which is coming into that quantization level range. Now next figure, it is your linear quantizer. So this linear quantizer, basically it is, you can see it from ranging from, it is what? minus Vp to plus Vp, that is minus peak voltage to plus V peak voltage. So what would be Vpp, peak to peak value? It would be Vp minus of Vp, that would be what? 2 Vp volt. Now this quantized pulses assume what? Positive and negative values. See, it is a positive and over here it is a negative values. So the step size between this quantization levels called what? Quantile interval, which is denoted by what? This small q. See, the step size between these quantization level, it is called quantile interval, denoted by small q. And when the quantization levels are uniformly distributed, over this full range, the quantization, it is called what? Linear or uniform quantizer. There are all L levels are there, and each sample value of the analog waveform is approximated with quantized pulse, and so that the approximation will result in error no larger than that of your plus q by 2 or minus q by 2, because we have assigned level q by 2, 3q by 2, 5q by 2, like this one. And the degradation of the signal due to this quantization is therefore limited to half quantile interval, that is plus minus q by 2 volt. So guys, today we have seen that is a sampling theorem. What are the different types of sampling techniques that we have seen? Natural, flat top, then we have seen quantization, why quantization it is important, and at the last we have seen that PCM, that is sampling, quantization, and then encoding. And we have seen that how encoding it has been done. We have seen the what are the types of quantization, uniform, non-uniform, how we are going to plot the graph of it. So it's all about today's lecture. This is the assignment. Please note it down, this assignment. In next lecture we are going to study delta modulation and adaptive delta modulation. So it's all about our today's lecture. Thank you very much.